So we are going to talk about our last two hypothesis tests for the course in the next couple of sections. The one we're going to do today is for comparing two unknown population proportions by taking random samples from each population and comparing the sample proportions that you get. The idea of the test is the same as it is for all of our tests. You start with an assumption that there's really no difference in the population proportions. And then you look to your data to see if you have enough evidence to doubt that assumption. So the basic structure will be the same. You start off with a null hypothesis of no difference. We typically have a suspicion about the alternative, right? We either think it's going to be one is greater than the other or less than the other, but sometimes we don't really know and we're just looking for a difference. But that picks out the alternative hypothesis of less than, greater than, or not equal to. So once you have your hypothesis set up, then you examine your data by calculating the test statistic. Now that's going to be a little bit more involved for this test than our others because we have two samples to keep track of. But once we calculate the test statistic, we use it in the same way as before, right? We take a look to see whether that test statistic or something more extreme than it would occur. Is it likely to occur just by chance, or is it such a rare thing that we would question our assumption of no difference? Right? So the test statistic, remember, is the statistic you calculate under the assumption of no difference. So if you get something really rare, then you doubt that assumption. Now we make that a little bit more precise by calculating the p-value, which tells us how rare getting a test statistic like the one we did or something more extreme would be if the null were true. So test statistic will be a little harder to calculate, but once we have it, we use it the same way as before. So we use it to get a p-value that tells us the probability of getting our results or something more extreme if the null is true. And then we compare that p-value to whatever our pre-assigned significance level alpha was. And if the p-value is less than alpha, that means our results were too rare to be plausibly attributed to chance. In that case, we would say we have statistically significant results and we would reject the null in favor of our alternative. Okay, so that's the structure. It's the same as before. There are a couple of complications with the two proportion test, the two sample proportion test. So we're going to take a look at those as we go through example one from the notes. It might be helpful to have the formula sheet ready. The two sample proportion test appears on the formula sheet. We didn't use it in the last exam, but you will use it on the final. Okay, so we are interested in comparing graduation rates among high schools. We're thinking about public schools and private schools, and we want to see if there's a difference in the graduation rates. So we've taken the graduating class from the public school, and out of 483 potential graduates, 449 graduated. So we would consider a graduate a success, and that is a sample proportion of 0.93 with a sample size of 483. So for that sample, I've denoted it with a subscript 1. So that's the first p-hat, or p-hat 1, and the first sample size, or n1. For the private school, we had 295 potential graduates and 286 graduated for a p-hat 2 of 0.97, right? We get a different sample proportion for the private school. The sample size for the private school was 295. So we need to set our null hypothesis. The null, as before, always is a statement of equality about the parameters. So we assume that there's no difference in graduation rates overall in public and private schools, so that our proportion P1 and P2 are the same. Now this is where the two proportion test gets a little different than before. Because if we assume the populations have the same proportion, then the best estimate for that proportion is what's called the pooled sample proportion. So if we assume that public and private schools have the same population proportion, then we should use all of the graduates divided by all of the potential graduates to estimate as well as we can the unknown population proportion. So we're going to call this the pooled P hat. Pooled means we put both samples together to estimate the population proportion P. And we do that because we're assuming both populations are the same. So the total successes would be the 449 from the public school plus 286 from the private school. Total potential graduates, 483 for public, 295 for private. Do those two additions and then divide them, and you get a pooled P hat of 0.945. Okay, so that's what we use as an estimate for the overall population proportion for both public and private, because of our assumption temporarily that they're not different. All right, now in the statement of the example, there's no leaning one way or the other for how we think private and public graduation rates compare. We're just looking for a difference. So our alternative hypothesis is that P1 is not the same as P2. That makes it a two-tailed test. And then in part D, we're supposed to explicitly check the requirements for the test. And here we're going to see that maybe this doesn't quite fit all the requirements. It's an example, so we'll use the test anyway. But first off, we have to have randomly selected samples. And we don't really have that here because it kind of sounds like there's like one public school, one private school, and we're just going to compare the two. I guess what we could say is that we could view this particular graduating class as kind of a randomly chosen graduating class from all possible graduating classes. Still, this seems more like a convenience sample, right? Just getting the current graduating class from the one public or one private school. It's more of a convenience sample than a random sample. So that one's doubtful, but we're going to press on anyway. And then the samples have to be independent, and I think there we're okay because we're just trying to make sure that the folks that we select in one sample don't affect the ones that we select from the other. And that's okay here. And finally, we have to have enough successes and failures in each of the samples. All right, so there's a little bit to this. In general, if we had a one-tailed test, you need 10 successes and failures in each of the samples, which we wouldn't quite have because, well, for the public school, we're okay. 449 successes and what is that? 34 then are failures in the statistical sense. And then we've got 286 successes for the private school and 9 failures, then that would narrowly miss the cutoff. But we're saved in this case because we're using a two-tailed test. And for a two-tailed test, the requirement is less strict, and we only need 5 successes and failures for each sample, and that we're okay with. All right, so some of these assumptions maybe are a little iffy, but we're going to go ahead and continue the example. All right, so the next step is to calculate the test statistic. So we have sample proportion 1 minus sample proportion 2, and then in the square root, in the denominator, that's the pooled sample proportion, where you take all samples together. So when we plug in our numbers, right, the 0.945 is from the pooled estimate, the p hat 1 is from our first sample, p hat 2 from the second, and then the sample sizes, N1 was 483 and N2 was 295. So you've seen that I plugged them in here. The rest is calculator work, which right? Can be a little tricky if you're trying to do it all in one go, but I get minus 0.04 divided by 0.0168, which is a negative 2.37 for my test statistic. We're using, this is a z-score, and so this is, because it's a two-tailed test, we're looking on a normal distribution for area to the left of minus 2.37 plus the area to the right of 2.37. To find the p-value, we need that total area, which we find by doubling one of them, because the two areas are the same. So I took twice the probability of getting a z-score less than or equal to minus 2.37. Using StatCrunch, I get 2 times 0.009. So I'll go through how to do that. Well, this is just what we've been doing before, but I'll do a StatCrunch video as well. So the p-value is 0.018. What that means is, if there was really no difference in high school graduation rates between the public and private school, then we would get a sample difference like the one we saw, or something more extreme, about 1.8% of the time just due to chance. So it's a really small chance. We would consider this a pretty rare event. So even without looking at the alpha, we're in pretty good shape here to reject the null. Right? But to make it official, we compare it to the alpha, which is given as 0.05. That's our threshold. Any p-value bigger than alpha, we fail to reject the null. Anything smaller represents statistically significant evidence against the null, so we reject the null in favor of the alternative. Right? So in this case, we would reject our initial assumption that there's no difference in graduation rates and conclude that in fact there does seem to be a difference, and our samples indicate that the private school has a higher graduation rate than the public school. So that's example 1.